Yeah, hello. This is the first of the demo recordings for the GATE course. Now, this recording is on the topic of Introduction to Mechanics of Materials, more popularly known as SOM, Strength of Materials, right? Now, in this lecture, we would be discussing about why actually we need to study this subject. What is the need to study this subject, and then we'll look at some basic concepts in this subject. Now, first let's start about why do we actually need to study the mechanics of materials. Let's name this session as the introduction. This is the introduction to, let's take the more popular name, that's SOM, Strength of Materials. Now, see, all engineering structures and machines such as planes, automobiles, bridges, spacecrafts, etc. are usually formed by connecting various parts or members. Okay. Now, in most structures or machines, the primary function of a member is to support or transfer external loads that are acting on it, and that too without failing. Now, failure of a member may occur when it is loaded beyond its capacity to resist fracture, general yielding, or excessive deflection. Now, excessive deflection can also be termed as instability. This means that we are actually analyzing the failure of a material in this subject, how it fails. Okay. Now, failure does not necessarily means that it is fracturing itself. It is breaking up into two different parts. That's the ultimate thing that can happen to a material when it is under service. But as an engineer, we do not want our material to fracture itself. Okay, so we'll be studying at different modes of failure. We can also name it as different modes of failure. Okay, we'll be looking at what the yielding is, etc. Now, moving on, when we are talking about loading of different members in a structure, then we talk about how actually this member is loaded. Okay, so if we look at the very elementary studies of strength of materials, we will see that members are subjected to basically three kinds of loading. So the first kind of loading that a member is subjected to is an axial load. Okay, the axial load, as the name suggests, it acts along the axis of the member. Okay, the second kind of load that acts on a member is a bending load. Now, we'll be going into much more depth for these terms, but for the moment, let's just see, or let's just assume that an axial load, assume is also not the appropriate words. Let's just focus on the literal words that are here. Axial means that something which is along the axis. Okay, that's your axial load. A bending load is something which bends a member. Okay, bends mean it becomes curved. A curvature sets in. Now, the third kind of load which usually acts on a member is torsion. Torsion, or more popularly known as twisting. Okay. Now, these three kinds of loads that are acting on different members, and then we'll be studying the effect of these three kind of loads on different materials, okay, and how these three loads actually bring about failure, how a material fails. Okay, now let's move on. Let's first of all describe an axially loaded member. Now this is an axially loaded member. Now let me just give you a very simple diagram for an axially loaded member. Let's draw the section of a shaft. Okay, this is the axis. Now this is a small shaft, a section of a small shaft. Let's give the length of this section as L. Now if I apply a load along the axis of the shaft like this in both the directions, this load is P, then this becomes an axially loaded member, because the load is acting along the axis. This is acting along the axis. Okay, great. Okay, then what actually happens when you apply this kind of a load, that is an axial load, onto such member? Okay, we'll come to that in the next slide or in the next lecture. Let's first of all describe all three kinds of loads that we have. Okay, the first is axially loaded member. Moving ahead, we have torsionally. Let's first go to the bending. Let's go to the bending of the structures or members. So this load, we'll talk about a bending load. Okay, now bending load means a load which bends or produces a curvature. Or it produces a curvature. Okay, let us just visualize this kind of a load by drawing a small beam. This is a small beam. Okay, and let me support it at this end, and let's load it at the middle. So if we name it, now this is support 1, this is support 2, and this is your load. Okay, so when you have such a structure and the structure is supported at its two extreme ends and is loaded at the middle of the length, then this structure would tend to bend like this. Okay, this will happen to bend like this. So this is the curvature that I am talking about. This is the curvature that I am talking about. Okay, it bends. So as you can clearly see that by applying a load on such a member, okay, we are actually bending it and giving a curvature to it. Now that the more theoretical definition of it is that a bending load is acting perpendicular to the axis of the member. If I draw the axis of the member, the axis is like this. This is the axis. Okay, but the load which is acting on the member is actually perpendicular to the member. Okay, so such a load is also known as transverse load. Okay, so a transverse load is a load which is acting on a member in a direction which is perpendicular to the axis of the member. Understood? So normally we associate bending with transverse loading condition. I hope it is clear now. Right? Moving ahead. Let's come on to the last kind of load that we talked about in the first slide. It was torsional load. Torsional load, or more commonly known as twisting. Now what is this? Now twisting is brought about by providing a rotationary motion or a rotational motion to a member. More commonly you give rotational motion to a shaft. Okay, so twisting is produced by rotating a shaft. And when you try to, or when you actually rotate a shaft, you are applying a torque. So when you apply torque onto a shaft, what happens? It comes under torsional loading. If we have to, visualize it, let us take a shaft, and this shaft is of a circular cross section. Okay, and let me just draw the side view for this. This is the front view, the elevation. Let me draw the side view. If I draw a side view for this shaft, okay, this is how you'll see it. Now let me draw the axis for it. If I draw the axis, let's say this is the axis. Now let's draw the axis or the two center lines onto the elevation as well. Okay, now what are we doing actually in this? We have fixed one end of the shaft onto a wall, let's say, and the other end is free. Now I'll be providing a rotational motion to the torque on its free end. So I'll be giving it a torque on the free end and trying to I'll try to rotate it like this. I want my shaft to turn in this direction. Okay, let us now assume a point. Let's take this point. Let's name this point A. Now this point can be visualized in the side view as this point. Okay, now on the side view assume another point on the axis as point B. Okay, I hope it's clear. Let's readjust our size of the arrow. Let's just keep it like this. Okay, now when you're turning it, let's come to the elevation again. When you're trying to turn it by applying a torque T on the free end of the shaft, this point A will move here and will come to a position A dash. Okay, so if I visualize it on the side view, it will be somewhere here. Let's say this is A dash. Okay, but this point cannot move because this point is fixed. This means this fiber which is along the axis will become like this. So there will be some distortion which will be produced in this shaft or the fiber of the shaft. Okay, this kind of loading is called twisting. Okay, we'll look into the details of twisting in the subsequent lectures. So the main aim of this slide was to look into the subject of strength of materials or mechanics of materials as to why we study it. So we study it by to analyze the modes of failure, how actually a material fails, how it actually responds to certain kind of loading. Now what are kinds of loading we having? We are having three kinds of loading. The first is your axial load, the second is your bending load, and the third is your torsional load. Okay, now let's now move on to some more elementary concepts of this subject. Let's go on to analyzing what is stress. Now what actually is stress, because we'll be dealing with this term on a huge basis in this subject. Now what is stress basically? If you go on to the theoretical definition, the theoretical definition says it is the internal resistance of a material to external deforming load. This means when you are actually trying to deform a body by applying a load, this means whenever you are applying load onto a body, what happens? It deforms. Let's just make a little algorithm here. Let's take another ink and so that we can differentiate it. So we have load. When you apply load onto a body, what happens? The body tends to deform. Okay, now anybody or anything has a certain amount of inertia, or they all have inertia. So any substance or any material which you are trying to deform would not want to get deformed. Okay, so the internal fibers or the fibers of the material will start producing a certain resistance to that deforming load. Okay, so that internal resistance, so I can just continue. I'll continue with the algorithm. So you apply load onto a body, it tends to deform. So now no material would want to deform itself. So that tendency of resisting will produce a resistive force which will oppose the deforming load. Now that resistance is called stress, or it will produce stress. So I'll write down here the resistance offered by internal fibers of material, and if I take it as per unit area, I will get something which is called stress. Understood? This means if I go into a more pictorial representation of this, okay, a more pictorial representation would tell me that if this is my material, let's take a small bar, let's draw the axis. We are taking an example of an axially loaded member. Now if I'm trying to pull it apart by applying an axial load like this, I'm trying to pull it apart. I'm trying to deform it. So what will happen? There will be an internal resistance which will be offered by the material. It does not want to get deformed. It hates to get deformed. Okay. So if this resistive force, let's name it R. Okay, and let's take the cross section area for this member. Okay, let's draw this cross section area like this. Let's have this. So this is the cross section area I'm talking about. This cross section area can be denoted as AC. Okay, so if I take this resistance per unit cross section area, that would be the mathematical expression for stress. Okay, so as you can see from the equilibrium that P is equal to R. So stress mathematically can be given as resistance per unit cross section area, where the resistance offered by the material in this case is equal to the load applied onto the material divided by the cross section area. So this is the mathematical definition of stress. Okay, now moving ahead, let's look at the mathematical units or physical units for the quantity stress. Now the stress quantity is mathematically denoted as load upon cross section area. If you look at the units for load, normally units are denoted, the loads are denoted in the units newtons. Okay, so N divided by this is meter square if we take SI units. Okay, now this means stress can be denoted or can be expressed in newtons per meter square. So 1 Newton per meter square, that's your stress, can be termed as 1 Pascal. Okay, this is Pascal. Now we don't normally use meters or SI units in engineering. We normally use metric units in terms of length. Okay, so I can say that if I want to use metric units, I would like to use millimeters. So 1 meter is equal to 10 to power 3 millimeters. But I'm not using meters, I'm using meter square. So I would like to square it. So this would become 10 to power 6 millimeter square. Okay, let's move it a bit. Okay. Continuing. This means if I replace the meter square in the denominator by this, so I will get 10 to power 6 millimeter square, and this is equal to what? This is equal to 1 Pascal. Now you take this value and you shift it on that side. Okay, so you will get 1 Newton per millimeter square is equal to 10 to power 6 Pascal. Okay, now what is 10 to power 6? 10 to power 6 is mega. So quantity expressed as 10 to power 6 can be termed as mega. This means 1 Newton per millimeter square is more commercially popular as megapascal. Okay, so 1 megapascal is equal to 1 Newton per millimeter square. You can remember this for the conversion rate or for the conversion ratios. What if the stress is given as gigapascal? Now giga is 10 to power 9 pascals. Okay, this is equal to 1 kilonewton per millimeter square. So just remember these two conversions, that 1 megapascal is equal to 1 Newton per millimeter square, and 1 gigapascal is equal to 1 kilonewton per millimeter square. Okay. Now, as we have discussed about the stress, that is the resistance offered by the internal fibers of the material per unit cross section area, let's look at the different kinds of stress that we have. Okay. Now, the first kind of stress is your tensile stress. The tensile stress is denoted as sigma and parenthesis T, sigma T. Okay. Now, this arises, or this comes into picture when we are having tensile loads. What are tensile loads? Tensile loads are loads which are trying to pull a body. You're pulling a body, so tensile loads can be represented as pull loads. You're pulling a body, that's a tensile load. Okay. So if I draw a diagram, let's take this and let's draw a diagram. This is a bar. More importantly, draw the axis. Okay. And let's now represent a load onto this kind of a load, P. Okay. So this is a tensile load. It is trying to pull apart a member, or we can say that it is trying to increase the length of this member. Okay. So when you have a tensile load, the length increases. So the stress which is produced for such kind of a loading is tensile load and is denoted by P upon cross section area. The mathematical formula remains the same. Okay. As it is trying to increase a quantity, that is length, so a tensile stress is regarded as a positive stress. So whenever you see plus sign, it indicates a tensile loading condition. Okay. Let's move on. Let's go on to the second kind of stress we have, that is your compressive stress. Compressive stress. Now, compressive stress is denoted by sigma C. Now, compressive stress comes into picture when we have a compressive load. Now, what's a compressive load? Compressive load can be associated with something in which we see that the body is being pushed. So you're pushing a body from two sides, so it can be termed as push load. Okay. So if I have to draw a diagram for it, how would it be? It would be something like this. Let's again draw this bar. I have this bar. Let's not forget to draw the axis. Now it's pushing it. So if you push it, it will be in this direction, P. In this direction, P. Okay. Now let us have the length for it. The length is L. So now if you are applying a compressive load onto it, the quantity of length, this value, this would decrease, isn't it? So we can say that the compressive stress tries to or tends to decrease the length of a member. Now let's look at the mathematical formula for compressive stress. This is same. The mathematical formula is same, but the only change that this value sigma C is taken to be a negative stress value. Just a minute. Is taken to be a negative stress value because the length is decreasing. If something decreases, we tend to treat it as something which is not good, negative. Okay, so compressive load decreases the length of a body, and the stress associated with that kind of load is also regarded as a negative stress. Okay, we have discussed about the units for stress value, that's megapascal. Okay, now let's go on to the next slide, which talks about the third kind of. Okay, before going on, let's look at the two stresses that we recently talked about, that was tensile and compressive. In both the cases, the mathematical formula was exactly the same. The only difference was that the tensile load was considered to be as a positive load, means a positive stress, and compressive load was treated to be as negative load, this means a negative stress. But in both cases, the load was axial. Okay, so I can state that for sigma T and for sigma C, both the stress values that was applied was axial. It was an axial load. That means it was perpendicular to cross section area. This is one concept that you need for sigma T and sigma C. Understood? Right, now this was the first of the videos for the series for the subject of strength of materials. The next series would be, or the next video would be, a continuation of this lecture that would cover the topics of strain and some elastic constants, but of course the most important of all, the stress strain diagram. Okay, see you on the next lecture. Bye bye.